Zero trust has been the buzzword in IT security for years, but what happens when you try to apply it to power plants, water systems, and factory floor control networks? In April 2026, CISA, the Department of War, the Department of Energy, the FBI, and the State Department released a joint paper on how to adapt zero trust principles to operational technology, OT, without breaking safety or uptime. In this video, I'll break down what that actually means, why the standard IT playbook doesn't work in OT, and the concrete steps you can start taking today. OT used to live in isolated control rooms, often air-gapped or manually operated. Today, those same systems are increasingly connected, remotely monitored, and integrated with IT networks. That convergence massively expands the attack surface. Threat actors have already shown they can leverage IT to get into OT by stealing Active Directory credentials, abusing remote access, or riding in through compromised vendor updates. The paper calls out how groups like Volt Typhoon and others have used living off the land techniques and OT-specific capabilities to quietly position themselves in critical infrastructure environments. And unlike pure IT, a cyber incident in OT doesn't just knock out email. It can shut down power, damage turbines, pollute water, or threaten human safety. Zero trust in IT is all about never trust, always verify, strong identity, continuous validation, and tight segmentation. Those ideas still apply in OT, but the constraints are different. First, availability is king. OT systems run 24/7, directly controlling physical processes and can't tolerate frequent reboots, aggressive policy pushes, or surprise outages. Second, you're dealing with legacy, insecure systems that may be decades old, run unsupported operating systems, and use fragile proprietary protocols that can't handle active scanning or endpoint agents. Third, logging and monitoring are often minimal, and the teams are split. OT engineers care about safety and reliability, while IT and security teams push for more controls. The paper stresses that zero trust for OT only works if these teams collaborate and share risk decisions. The first pillar the document hits is govern. Before you buy tools, you need governance that matches the reality of OT. That means clearly defining who owns what. Plant managers, operators, engineers, integrators, vendors, and OT-focused security staff, all with documented roles and responsibilities. The guidance also calls out procurement as a strategic lever. You can't magically retrofit modern zero trust onto 30-year-old controllers, so you need to use new purchases to move toward gear that supports logging, secure protocols, and identity-aware access. And because vendors and third parties have so much access, the paper leans hard on supply chain and third-party risk management. Things like SPOMs, vendor vulnerability practices, and tightly controlled remote access. Zero trust for OT starts with a solid identify function, comprehensive asset inventory, configuration management, and understanding cyber-physical consequences. Unlike IT, you often can't just blast the network with active scans. The document recommends passive monitoring and OT-aware discovery to avoid knocking fragile devices offline, combined with carefully scoped active scans where you know it's safe. Once you have an inventory, the authors push for formal configuration and change management via a management of change process, with engineering, safety, operations, and maintenance all reviewing proposed changes. They also stress risk assessments and threat modeling that explicitly include physical impact, cascading failures, and mission consequences, not just data confidentiality. That's what drives where you apply the strictest zero trust controls. On the protect side, the paper leans heavily into layered segmentation and identity-centric access. OT has always segmented, but here they differentiate IT segmentation from OT segmentation. IT cares more about data. OT segmentation is about protecting physical processes and maintaining safety and reliability. Think firewalls, jump hosts, secure gateways, and data diodes, creating zones that can operate autonomously, with controlled, often one-way flows to the rest of the network. Then you add micro-segmentation, finer-grained policies between business units, between control and safety systems, or even down at the tag or data point level. On identity, credential, and access management, the guidance is blunt. Don't just hook OT straight into your IT identity infrastructure. Use separate forests or domains, avoid direct trust relationships, and design for emergency or break-glass access that doesn't break safety. They recommend privileged access management, credential vaulting, session recording, and just-in-time access where the technology supports it, plus compensating controls, segmentation, monitoring, physical safeguards around legacy gear that can't take agents or strong auth. Remote access gets its own focus. The document pushes hardened jump hosts in a DMZ as the only way in, with MFA, patching, monitoring, and ideally OT-specific features like session recording and anomaly detection. The paper also dives into secure communication. Many OT networks still run unauthenticated, unencrypted protocols. The authors argue integrity and authentication are usually more critical than confidentiality, because encryption can add latency or complexity that hurts safety. They suggest using secure protocol variants like BACnet, SC or DNP3 SAV5 where possible, or wrapping legacy protocols in TLS-enabled gateways and encrypting traffic that crosses untrusted networks or third-party links. For patching, the guidance is realistic. OT patching follows maintenance windows and safety constraints, not monthly IT cycles. They recommend structured decision frameworks, prioritizing edge devices and remote access systems, and using isolation or virtual patching when you can't patch quickly. On Detect, the document talks about continuous monitoring across IT and OT boundaries, using baseline-based detection and specification-based detection, essentially modeling what normal and valid behavior look like in your process. They discuss EDR challenges in OT, old operating systems, embedded devices, and warranty constraints. So they suggest lighter weight telemetry, strict scope on blocking, and staging servers for updates in isolated networks. On Respond, they emphasize OT-specific incident response planning, clear isolation procedures, decision trees for when to shut down or segment systems, and joint playbooks between operations, engineering, IT, and security. Containment in OT is about balancing aggressive security actions with uptime and safety, often using physical security, least privilege logins, and carefully planned segmentation rather than quick pull-the-plug moves. For Recover, the authors highlight comprehensive backups, not just data, but OS configs, application logic and engineering files, and regular testing of restores on dev systems or via file integrity checks. They tie all of this into business continuity planning, with defined recovery, time objectives and procedures that account for cyber incidents, not just physical outages. At the end of the day, this paper makes one thing clear. Zero Trust for OT isn't a product you buy or a checkbox project. It's a long-term, collaborative shift in how you manage risk in environments where safety and uptime are non-negotiable. Success comes from accurate asset visibility, realistic risk modeling, layered segmentation, tailored identity controls, and tight partnerships between OT engineers, IT architects, and security teams. If you want to dig deeper, the document aligns with a NIST CSF 2.0, CISA's Zero Trust Maturity Model, NIST SP 800-207, and ISA IEC 62443, so you can plug it straight into your existing frameworks. Let me know in the comments if you want a follow-up video focused just on practical zero trust, quick wins for OT environments.